All right, how do we use genetics to solve crimes? If you like this, you might want to take forensics your senior year. But a lot of us know from TV that DNA can be used to identify, it could be a victim, like a body found in the Hudson River, and they don't know who it is, or it could be to identify the perpetrator, like the criminal in a crime. So first of all, you got to get some DNA. So DNA can be collected from any body fluids, so including blood that was left, the saliva that was left at the crime scene, even semen if there was sex, like rape at the crime scene. So they can collect DNA from any of that. Also, if you had like that body that was found in the Hudson, there have been bodies found in the Hudson, a lot of rivers. You could get like a hair sample. You could say like, I think it might be this girl. Let's take a sample of hair from her old hairbrush before she disappeared from her college dorm or whatever. It could be, you could take it from her toothbrush. There's some saliva in there. If all that's left of the body is teeth, you could get sample from there. Sometimes like skin, like sometimes if the victim fought off the criminal, there's the criminal's skin is under the victim's fingernails. So lots of different places. You're just trying to get some cells of either of the victim or of the criminal. So once you've collected that DNA, what do you do with it? Well, you do gel electrophoresis. So what you do is you literally drop the people's DNA into some gel and you electrify it, which is why it's called gel electrophoresis. So there's like a few different wells, like you can see here's like a little kind of an eyedropper, but like a big sciencey one. I think we call it like a micropipette, but they're dropping some DNA into this well and then some more DNA into this well, DNA into this well. So maybe this is the DNA from the crime scene, and maybe this is the DNA from suspect one, or maybe it's the DNA from if we're trying to identify like a dead body in the Hudson, there might be like, we think it was this missing girl and we have her hairbrush, so we have her DNA. And maybe this is the DNA of suspect 2. Okay. And then what do we do to it? Well, we actually before that, we took the person's DNA and we actually chopped it up into little bits using these things called restriction enzymes. So we chop the DNA into little pieces, and it's like the enzymes kind of choose where to chop. We program them like anytime you see an AATT, I want you to go ahead and chop. So they go ahead and chop every time they see a certain code, they chop. And then we put that chopped DNA into the gel, and then we actually electrocute the gel. And DNA is negative, so it does move. We put the DNA in over here, and it is negative. So when we electrocute it, we end up making like a positive end. You know how batteries have like a positive and negative end? So we electrocute it, so this is the positive end of the gel. So positive and negatives attract, right? Opposites attract. So the DNA starts like wiggling through the gel because it's getting electrocuted and it's attracted to the positive. And what happens is the big clunky ones don't move as far. The big DNA kind of stays back here, and the little DNA pieces go further. And what you end up with is like these bands, this like banding pattern of the way your DNA fragments separated out, which I don't know who figured this out. It's really smart. So this is what it ends up looking like. Like this is where the DNA started down here, and it went like blah, 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 and it moved further and further and further. The bigger pieces stayed here, the little pieces stayed here, and you end up with like a distinct pattern of like the bands that your DNA makes. So you can see the blood stain from the crime scene has this pattern. Big fat, then kind of this, then this, then this, then this, and this. And then you can say, well, who does it match? Who has that same particular banding pattern? If you look, like this one's not matching, right? That's not the same. These are kind of similar. That one's not the same. Okay, if you look, this one right here, if you look at the banding pattern, it is very similar. So if you ever watched a crime show and they said like, oh, the DNA had 15 matches, it meant there was like 15 bands that were the same. All right. So that is how we figure out, like, we compare two people's DNA. We don't look at every bit of it. We chop it into little bits. We put it through electric gel. it moves into this pattern, and then we compare patterns. Kind of weird, huh? We have now come up with a more sophisticated technique. I don't know if they're using it yet, but now we actually can actually look at someone's DNA code. Like it used to be like that took years for us to like figure out the letters in like one person's DNA. But now I guess we can do it faster. So now they're starting to actually look like, okay, instead of just looking at like these chunky patterns going like, okay, this person's DNA is AAGTCT. Okay, we have an exact match. So that's kind of like the DNA matching in the future. But this is what we've been using so far. All right, so what were the steps to that? It was step 1, somehow collect some DNA. Step 2, use the gel to separate the DNA into like a little particular banding pattern. Step 3, compare the banding pattern of the DNA sample to like a DNA that you already had. So you might say, oh, this unidentified body from the Hudson matches the hair from the hairbrush of this girl who disappeared last May. Now we know that girl who disappeared actually is dead in the Hudson. She's not missing anymore. So I guess it brings comfort to the family and we've identified the body. Or it could be, oh, I found this blood at a crime scene and it matches this guy who I kind of thought might have done it. He's a suspect. Okay, now we know he was at the crime scene. So another cool thing about genetics and DNA is that you can solve crimes with it.